Right. Hope you got your midterm marks, right? Uh, actually, okay. I actually could not. I still didn't have the time to take a look at your midterm paper because I also have another midterm there. But anyway, so your midterm is gone, right? So don't dwell on it too much, right? So from your midterm, you learn what didn't go wrong or what went well, and then try to adapt it to your final because the final is still a large weightage, right? It's very significant, right? So the final is still there, right? And for those that did well, so if you got like at least 90%, right? So you should send me a message so that I can get you probably, right? Okay. Okay, I will not take a look at your marks, right? I usually don't take a look at students' marks, right? Okay, usually. Okay, so let's start. Today's greedy, right? Today we talk about greedy algorithms, right? Right. So greedy algorithms are similar to DP in many ways, right? Okay, but there's one significant difference, right? So in DP, like we talked last week, right? So DP has many sub-problems, right? But we don't know which sub-problem leads to the optimal solution, right? We don't know which sub-problem leads to the optimal solution. Okay, so because we don't know which subproblem leads to the optimal solution to the original problem, what we do is we try all the subproblems, right, and see which ones lead to the optimal solution, the original problem, right? So again, DP has many subproblems because we don't know which of the subproblems lead to the optimal solution of the original problem. What we do is we try all the subproblems, right? For example, last week we did what? For example, in the polygon, right? The polygon, what we did was we went through every single other point that the side xy joins to, right? Right? Can you remember in the DB problem? But in the greedy one also has potentially many subproblems, but with the difference is that with absolute certainty, you can point to one subproblem, okay, and say that this one will lead to the optimal solution to the original problem. Right? That's the major difference between greedy and DB, right? Okay, so this one subproblem is a caveat, right? So what I mean by one is like a constant number usually, right? In here, you need to try all the subproblems. Here, like one or two subproblems that you require subproblem will lead to optimal. But to make the distinction very clear, DP has many subproblems many subproblems, right? Because we don't know which lead to optimal solution, we try all subproblems, right? So greedy is different. So the greedy also has many subproblems, but with absolute certainty, you can point to one subproblem and say that this will lead to optimal solution, right? And to prove this choice of this subproblem will lead to optimal solution, we use this technique known as the exchange argument, right? Okay, so the exchange argument is used to prove that this one subproblem will lead to the optimal solution to original problem. Okay? That's what exchange argument is. Okay, so and also to prove exchange argument, you need a formal proof, right? So okay, you need a formal proof of the exchange argument a formal proof of the exchange argument is needed, right? So let's see how we do that, right? So previously we had optimal substructure for DP, but now we have the exchange argument, right? Okay, so this is a code by Stephen Harding, right? So for a theory course like CS3230, the exchange argument. So this, what he means by this is the exchange argument, right? So the exchange argument is the most important part, right? In programming contests involving greedy problems, teams don't actually prove that the exchange argument works usually. What they do is they just implement it and hope it works. If it works, then it works. So that proof is known as proof by acceptance, right? But we don't have proof by acceptance, right? So what we're going to do is prove this formally using some techniques that I will show you, right? Okay. So crucial things to master in order to master greedy algorithms is one is optimal substructure that you already know, right? By cut and paste argument, so proved by correlation, right? And the next one is greedy choice. Okay, this greedy choice is proved by the exchange argument, right? Yeah. So one important thing is that greedy doesn't always work. So greedy doesn't always work, but when it does, it is really fast. Okay? Right. So to know when you can apply greedy, it requires development of your greedy sense, right? So you need to know by looking at a problem whether greedy will actually work on it, right? So you need to the only way you can actually improve your greedy sense is to do by practice, right? Okay. So question number 1. So let me check who's presenting to do. Gary is here. Okay, so Bob wants to burn music files in CD. PC is 100 megabyte capacity and can have at most 2 files per CD. files cannot be split across CDs, and so these are the rules, right? And given a set A of file sizes, define min CD A as the minimum number of CDs needed to burn CDs. Need to burn the files. Okay. Okay, so Bob wants to use the least number of CDs to fit his music collection. Okay. The first question. So which of the following correctly describes an optimal substructure property of the problem? Right? Okay, so optimal substructure is not new to you because we already discussed in DB, right? Okay, so how do we begin answering such questions? That means how do we begin answering optimal substructure proof kind of questions, right? So how do we begin those proofs? Okay, so let's ask Gary. So Gary, how do we begin such questions? So how do we prove that optimal substructure works? Right? That means this problem exhibits optimal substructure. Sorry? Yes, okay, Kata base. So that's proof by contradiction, right? Okay, so we begin by saying, so consider an optimal solution to the problem. So that means we have to first begin with some optimal solution to the problem. Okay. So for example, I just consider this solution to the problem. Yes, just to illustrate, right? Okay, next step is to suppose that the optimal substructure doesn't hold, right? That's cut and paste, right? Okay. So next step is to suppose for the sake of contradiction that the subproblem was not solved optimally. Okay. So here the problem is to burn these CDs, right, into disks, right? So this person has burned these two files into this disk, right? And then after he burns these two files into this disk, then he has these four files remaining, right? And then the way he solved that subproblem is to burn this disk into one, burn this file into one disk, burn these two files into another disk, and burn this file into a single disk. So this is how that person solved the subproblem, right? And suppose for the sake of contradiction that this subproblem was not solved optimally. Okay, so because we want to try and get a contradiction, right? Okay, so if this subproblem of burning these four files, so we have these four files, right? These whatever these files are, right? Suppose that this subproblem of burning these files were not solved optimally, then for example, how would it look like? Okay, then it would look like this, right? Then there exists a strictly better solution to the subproblem, right? So that means to burn these four files. That means we have these four files, right, with us, right? To burn these four files, then we can find some allocation with less CDs, right? For this subproblem. Okay, is that okay? Okay, is that okay? That's obvious, right? So we can find some allocation, right, with less series, right? So for example, let's say this subproblem can be solved with only two series. That means you can burn it like this. So suppose that this is possible because again, right, there exists a better solution to the subproblem. If that subproblem was not solved optimally, right? If this is suboptimal, then there must be an optimal solution, and this is one of them. Then we cut and paste. We use this. We use we use this allocation of files onto CDs with this original allocation to get a strictly better solution, right? Because in this way, we combined this allocation of the subproblem with your initial choice, and we use only 3 CDs. Previously, we used what? How many CDs? 4 CDs. But we claim that this solution was optimal, right? But then here we have a solution that only uses 3 CDs. So then how can this be optimal, right? Right. Therefore, that's a contradiction. Therefore, in any optimal solution to the problem, any subproblem must be solved optimally. Okay. Okay. Any questions? Okay. I mean, this should be very, very easy to understand, right? So I hope that there are no questions, right? Okay. So answer B precisely describes this. Okay. For any pair of files that so F1 and F2 in A that belong on a CD. Okay. Let's say these two belong on a CD in the optimal solution, right? Then the minimum number of CDs required to burn all those files is equal to 1 plus the minimum number of CDs required to burn the files that are not in A. That means you take away F1, F2. That means A out. I mean, so A take away F1, F2 are the remaining files. So you have to solve that problem also optimally. Okay, so you solve that problem optimally, and then you add 1. That means the 2 files that you actually burn on one CD, and then you have main CD A. Okay. Any questions? Okay. So it's very easy. So let's also go through the other answers, right? Okay, so our question was what? Here, right? So which of the following correctly describes an optimal substructure property, right? So here's another answer. Another answer is so let me quickly get this. Okay. So here was like the other answers, right? So we already discussed the B, right? So we have A. So A is what? For any pair of files F1, F2 that is in A, it holds that min CD A equals 1 plus min CD A take away F1 and F2. Okay, so that's obviously wrong, right? For example, what if F1 and F2 don't even fit together, right? So then they say for any pair of files, right? So that's also wrong. But there you can also construct an example, counterexample where you don't actually violate the constraint because here's a very simple example, right? So here, if we have A as 10, 20, 80, 90, and the optimal solution will be to pair 10 with 90 and 20 with 80. Okay, but so suppose that we use this strategy, right? For any pair of files F1, F2 in A. So suppose we chose that strategy. Then if you pair 10 and 20 together, okay, so 10 and 20 will be on one file, right? But then we have 80 and 90, but 80 and 90 cannot fit on one file. That means you need to fit 80 and 90 on two different files, right? So then we have on two different series. So then we have one CD, 2 and 3. So that's suboptimal, right? Okay, so if we do it like that, we would have to use 3 series, but the optimal solution is 2 series. So therefore, this claim that for any pair of files F1, F2 in A, that this holds is wrong. Okay, so you cannot pair any two files in A on a series and hope to get an optimal solution. I mean, it's obvious if that was true, then you don't need to even give this question as a tutorial question, right? Okay. Okay, so C is also obviously wrong. So what is C? If F1 and F2 are the largest and smallest files in A, then min CD A equals 1 plus min CD A take away F1 and F2. Okay, so let's ask Gary, right? So Gary, why is it obviously wrong with the answer? Why is C wrong? That means here, right? So we want to show which are the following correct described optimal subset. Now we know that this wrong. We know that this correct because that's what I showed, right? If F1 and F2 are the largest and smallest files in A, then this describes optimal subset. That means min CD A equals 1 plus min CD A take away F1 and F2. Is that correct? Yes. Yeah. So F1 and F2, yeah, they might not even fit on the same CD, right? Okay, so then these of course obviously wrong. Right. So next question, right? Okay. So now we have to prove the greedy choice. So this is the most important part, right? So we are going to prove the greedy choice. So okay. So now even in the exam, right? So if you're going to prove greedy choice, right? Greedy choice is actually it should come very naturally to you, right? The thing that you claim to be the greedy choice must be logical. Okay. In that way, greedy questions are a little bit easier than the DP questions. Okay. Because because in DP you need to figure out, okay, you have to solve all sub problems and choose the best one. Okay, so you need to prove also a little bit, right? But in greedy, okay, so you will see this when you do more practice questions, right? So in greedy, the greedy choice is kind of sensible. It's almost obvious, right? But of course, you need a bit of practice. But the greedy choice is after you have some practice, the greedy choice is very obvious, right? Okay, so here's my greedy choice. Okay, so out of the remaining files, you choose the largest file that's remaining, right? So you have burned some files, and then now you have some files that's still left to be burned, right? Out of those remaining files, you choose the largest file. Okay. And out of the remaining files that fit with this largest file, you choose the largest. Okay. So now you have a lot of files, right? So out of those remaining files, you choose the largest file because that file has to be burnt on some CD, right? Okay. Right. So when you choose that file, so that file will burn on some CD. Now you also have other files, right? So now we know the constraint, right? At most 2 CDs can be on one file, right? So our sense is to be greedy, right? To minimize the minimize the number of CDs used, right? So if we have burned this largest file onto a CD, then we should at least try to burn some other file with it, right? I mean, if we cannot burn, then fine. Then we just let it go. But if we can burn something, we must burn something with that file, right? Okay, you're trying to be greedy, right? So if you can burn some other file with this file, if it's possible, then what is the natural choice that you're going to choose out of all the files that can be burned with this largest file? obviously you will choose the largest file that fits with the largest file, this largest file, right? Because you don't want that, okay, you don't want that, intuitively I'm saying, right? So you don't want the largest file that fits with the largest, this absolute largest file lingering around anymore, right? Because that might obstruct some other file, right? Had you chosen that largest file to pair with this largest file that you chose out of the remaining files, then intuitively you know that you're better off, right? Because if not, that large file is still lingering around in the collection, right? That can obstruct some other files later on. Okay, so this is your intuition. So you need to build this slowly by slowly. But okay, let's prove that. Okay, so let's formally prove that. Okay, so just knowing that intuition doesn't mean that your answer is correct, right? So let's try to prove it. Yeah, okay, so you should see that it's sensible, right? It's very sensible thing to do, right? Okay, and I put a star here because so there's another greedy solution. So I'm going to present both of them. So the other one is very symmetric, but I'll talk about that later.
I want to ask about this one. For the second, like out of the remaining files, find the largest that fit the largest file. Wouldn't this be another ON? So this solution become an ON square.
So no, we are not talking about time complexity here. We are talking about whether this greedy choice is correct or not. So we are not talking about efficiency. Okay. So so first of all, we see this strategy is sensible, right? And the second one, does this mean we pick the two largest files out of the remaining files? You are right. Yeah. Does this mean we pick the two largest files out of the remaining files?
No.
Why?
Like because the second of it say that it must be fit to be compatible with the largest file.
Yeah. So the two largest files may not fit on a CD. Yeah. So let the proof begin. So pay close attention, right? So now we're going to prove this this greedy choice. That means this greedy choice is correct, right? Okay. So let's consider some. Okay. The keyword is consider some optimal solution. Oh, right. Why did I say some? Because this some optimal solution need not follow my greedy solution. Someone else solved the problem. Now we're going to look at that optimal solution, right? So keep in mind that this optimal solution, this OPT, need not follow my greedy strategy. Whatever I said was greedy, this opt may not follow that, right? And then our goal is that we are going to modify opt, okay, in one step to follow this greedy choice and not hurt the optimality of opt. So we have an optimal solution that someone gave us, right? If it follows greedy strategy for the first step, then we're done. Because we inductively prove this, right? If it did not follow our greedy choice for the step one, then we perform where we do an exchange, and okay, I'll talk about that later, but we perform this greedy step on OPT while not hurting the optimality of opt. Then what can we say? That means even if you do your greedy step, the optimality of opt is not hurt. Then that is safe. Then that means it is safe to do the greedy step. Okay, so if you do this inductively, right, that means you do the greedy step, optimality is not hurt. Then you again do it inductively. So I do another greedy step, optimality is not hurt. Again I do greedy step, optimality is not hurt. So you keep on doing this inductively until you reach 10. That means at the end, optimality is not hurt after you do all the greedy steps, right? Then that means your algorithm, which is completely greedy, is optimal, right? Okay. Okay, so let's do that slowly, right? So okay, so let's do it slowly. Okay, so in this optimal solution, the largest file, remember, now we're going to prove that our greedy choice is correct, right? So that has to deal with this largest file, right? So in this optimal solution, the largest file must be on some CD. Why? Because you have to solve the problem, right? So that means every file must be one, right? So there are two cases for the disk containing the largest file in OPT, right? So okay, so first consider the obvious one, the easiest one. The largest file is lonely opt. So that means in this optimal solution, the largest file is alone. Okay. Now, if there were other files that fit with this largest file, okay, so if there were other files that fit with this largest file, okay, so suppose that there were no other files that fit with this largest file, then I claim that our greedy choice is already correct. One. Yeah, doing it. Sorry. So now the first case is in this optimal solution, we are going to look at where the largest file is, right? So we look at this. We look at this case where the largest file is lonely. That means there's no one with this file in this disk. My question to you is, if there are no other files that fit with this largest file, then our greedy choice is already correct.
Yes, because when you choose the second disk, you filter by the ones that will fit.
Yeah.
So if there's none that fit, then the largest file will end up alone.
Yeah, that's correct. But another way of putting it is that so we choose the largest file, and then from the remaining files that fit with this largest file, we have to pair it with the largest this step, the disk that we choose in step 1, right? But there are no disks, right? So that means even in the optimal solution, you have this disk alone, and even in the greedy strategy also, we have this disk alone, right? That means the first step is the same as both strategies, right? Okay, yeah. So that means optimal also follows this OPD solution also follows the greedy strategy. That means this first step is same. Okay, so even if you do your greedy step, optimality of op is not correct because even OPD did this, right? Okay, so now a little bit complicated, not that much complicated. If there are other files that fit with this largest file, okay, so there are some other files that fit with this largest file, but they are in some other disk, so somewhere else, right? Okay, then obviously bringing any of those files from another disk and pairing it up with this disk, right, will not hurt optimality, right? Right. So if there were any other file that fit with largest file, then bringing it and pairing with this one will not hurt optimality, right? At best, then this number of disks will decrease. Okay, but it cannot decrease because we assume that it is optimal, right? Okay, so if there are other files that fit with this largest file, that means they must be in other disks, right? Then even if you bring one of those files and and put it on this disk with this file, then it will not hurt optimality, right? Of OPD. So in particular, that means you can also bring the largest files that fit with this file and pair with this onto this disk, right? Okay, so therefore, even in this case that we have proved this greedy choice, right? Okay, right. So it's very easy, right? So this largest file that fit with this file, okay, is not in this disk. It's in some other disk. So even if we bring it from other disk and pair it with this file, then obviously we will not hurt optimality because at best we can only decrease the number of files. Can we increase the number of CDs? No, we didn't use another CD, right? Okay, so obviously we didn't hurt optimality of op, right? Okay, very easy, right? So next one. Now, of course, the second case is that the largest file is not lonely in OPD. That means, okay, so now you have your largest file, right? Of the remaining files, right? So this largest file is basically this file in step 1, right? So this largest file, right, is not lonely in OPD. That means even in OPD, there is someone paired with this largest file. Okay, now the first case. If this file is the largest among all the files that fit with this file, then is a greedy step. Let's ask. This is a very easy participation point. So Kirtan, well, Kirtan, he didn't get the very easy participation point. Kirtan. Okay, Shenhong, right? Yes. Yes. So if this is the largest file out of all the remaining files, right? And then we see that this file is the largest file among all the other files that fit with this guy. Then is our greedy step done? That means there's a greedy step hold.
Yes.
Fine. So what was a greedy step?
Greedy step is like from all the remaining files that fit with this largest, you find the largest.
Yeah. So the first step was to, okay, out of all the remaining files, you have some at the absolute biggest file, right? And then out of the other files, without this absolute biggest file, you choose the largest one that fits with this guy, right? Okay, so here also we have the absolute largest one, and then this guy is the largest one among the rest that fits with this guy. Then obviously the greedy step is already done in opt. Then we have nothing to do. That means opt also does the greedy step, right? So that means the greedy step is safe. But of course, we have to choose, we have to do the harder one, right? Okay. If the partner of the largest file is not the largest among all the files that fit with this guy. Okay, let's consider that case. Example like this, right? So this one case, right? So we have the largest file, and the largest guy that fit with this file is somewhere else. Okay, and then the file that is currently on this disk is smaller than this guy. Okay. Then now again, right? We have to do the greedy argument, right? So that means even if you apply one step of your greedy argument, then it must not hurt the optimality of output. And I prove this by the extend argument, right? Okay. Again, right? So to prove the greedy step, you must use the extend argument. Always keep in mind extend argument for greedy, right? Greedy chunks. Okay, then Shen Hong, right? If I swap these two files, then will it hurt optimality or will it even hurt validity? Yeah, let's talk about validity. If I swap these two files, will the solution become invalid? Okay. Gary? So again, right? So this is our largest file, right? And the largest file that fit out of the remaining files that fit with this guy is somewhere else. So let's say it's here. And the file that is paired with this guy is smaller than this guy. Then if I swap these two files, will it hurt the validity of the solution? That means will it now become invalid? So the only way that it can be invalid is that the sum of these two files will be strictly greater than 100, right? So can that happen? Why? Yes, but okay, yeah, that's it, right? So by definition, right? That's all. Okay, so this is the largest file that fits with this guy, right? So that means this guy fits with this guy. So even if you bring this CD here, right, and then of course you have to bring this CD here, right? Then even if you swap it, right, then surely the sum of files of this guy and that guy must be at most 100, right? Because that is the largest guy that fits with this. Okay, right? And of course, even so, then afterwards, if so, then of course, then this guy will come on this CD. Then surely that guy must fit on that CD. Okay. Okay. So next question. If that's a bit of a stupid question, but can this guy fit on one CD? Yes. Yeah, right. Otherwise, the problem is intractable, right? Okay, the problem is tractable, right? I mean, if this guy fits on a CD, then surely this guy also must fit on a CD, right? Okay. Are we done? Have you exhausted all the cases?
No,
Yeah. What's the remaining case?
both disks have two files.
Yeah. Okay. So what if the largest file? So here, right? So we are going to prove the extends argument again, right? So we have this largest file, right? Okay. And the largest guy that fits with this CD is somewhere else, right? Let's say here. But okay, now we have to consider the case that even on this disk, there is someone else paired with this disk. Okay, recall this is the largest guy that fits with this guy. And on that disk, there is someone else also on this. On that disk, there's someone else also. So we have to prove that exchanging these two disks still will not hurt the validity, no optimality. Okay, so let's try to prove it. Okay, so even if you exchange, right, even if you bring this guy to here and that guy to here, I mean, even if I swap them, right, this will still not hurt the optimality, right, even if you do the greedy step. So let's see why. Okay, so let the largest file be L. So what's the largest file? It's L, right? And let its current partner be alpha. So this is L, right? This is alpha, right? Let the biggest file that fits with L be beta. So this is beta, and let the partner of beta be gamma. So this is L is alpha, this is beta, this is gamma. Okay. So the largest file that fits with L is beta, right? Now obviously, okay. So now what is our goal? We are going to prove that doing the greedy step will not hurt the optimality, right? No hurt validity, right? So that means swapping these two. That means bringing alpha to this disk, right? And bringing beta to this disk will not hurt the optimality or the validity. So we are going to prove that swapping these two is safe. Okay, the more what is okay. So in exchange argument, what you do is doing this greedy step or this exchange or swap is safe. That means it will not hurt the optimality, no validity, right? Okay, so now let's see what happens, right? So first of all, you must realize that L plus alpha must be at most 100, right? I mean, clearly they fit on one seed, right? And this value solution. And beta plus gamma is also at most 100 because again, this is a value solution and these two must fit on one seed. And we also know that alpha is at most beta. Okay, so let's ask why. Just to know that you're listening, right? Why is alpha at most beta?
Because alpha is smaller than beta.
Okay.
Is that like,
Yeah. Okay, so why is alpha small? I mean, yeah. So I ask you, why is alpha at most beta then?
oh okay.
You're saying alpha
It
is at
is
most
because of beta is the largest that fit with L, and then alpha also fit with L. Although alpha is smaller than beta.
Yeah. Yeah, correct. So obviously, of course, that's the reason why, right? Okay, so now if you swap the disk, then what happens? So then beta comes with L, then alpha comes with beta with gamma, right? So alpha will be with gamma, and then L with beta. Okay, so by definition of beta, L plus beta must be at most 100, right? Because this is the largest one that fits with L, right? Then L plus beta must be at most 100. Okay, so next one. And alpha plus gamma must also be at most 100. Yeah, what? Do you think? Why must alpha plus gamma be also at most 100?
Because they fit on the same disk. The same disk.
So alpha plus gamma is this, right? So how can you say that they fit on the same disk? Okay, I mean, you can see that they fit on the same disk, but like, how can you mathematically prove that? Okay, alpha plus gamma is at most 100. So very fun.
Wasn't it assumed in the original scenario?
So previously what I said was what? The original scenario was like this, right? Here we had alpha with L, right?
Alpha plus gamma.
Yeah, alpha plus gamma.
Oh, sorry.
Yeah.
Because alpha is less than beta.
Yeah.
And beta plus gamma is less than 100.
Yeah, correct. Right. Okay, so here we had what? Beta plus gamma is at most 100, right? And we also know that alpha is at most beta, right? So if beta plus gamma is at most 100, and then alpha is the number that is at most beta, then of course alpha plus gamma must be at most 100, right? Okay, right? Yes. So therefore, we have that L plus beta is at most 100 and alpha plus gamma is also at most 100. Then by doing this swap, we didn't hurt the validity of opt, nor did we hurt the optimality of opt. Therefore, this greedy step is safe. That means by doing this greedy step, you will not lose optimality. Okay. So now what we did was in every step we did in every possible case we check whether doing this greedy step will hurt optimality, and we realized that it doesn't. Then that means we can conclude that this greedy step is safe. It means in this problem, even if you do this greedy step once, you will not hurt the possibility of hurt the optimality of opt. Means when keep on doing this greedy strategy, and you will end up with an optimal answer because you will not hurt optimal, right? Okay, so next one. Okay, so the next one is equivalently. There's another way of doing this, right? So I talk about where you choose the largest file, and then out of the remaining files that fit with this guy, you choose the largest. But here's another one. We also can do like this. It's an equivalent mirror one, right? So we can choose F1 as the smallest file, and F2 to be the largest file that fits with F1 to put on a single CD. This is basically the same thing as before, except now you will choose the smallest files. Okay, so exact mirror values, right? Nothing much. And okay, so you can almost, I mean, the proof is exactly the same, just you have to mirror it, right? Okay. Right. So question number 2. Okay, so let's think about this one, right? So we have to choose the smallest one, and then out of the remaining ones, choose the largest one that fits with the smallest one and put on the same CD, right? So now let's look at this one, right? So assume that okay, so let's look at this first, right? And then they say assume any optimal solution contains a pair that is burned on a CD. Okay, then select all true statements about the problem. So we're going to go by this one, right? So first one, the smallest file must be included in some optimal solution. True or false? Would be
Four.
okay. The smallest file must be included in a pair in some optimal solution. Okay. This is true, okay? Because why? This is the greedy step. This is a greedy step, right? So we are going to look at this this solution, right? This is to solve the problem, right? So previously I talked about largest files and then choose largest file that guy put on a CD. But here let's look at this alternative solution, right? In this one, we choose the smallest one and the largest file that fit with that guy you put on the same CD. Then in some optimal solution, then of course then F must be the smallest file must be included in a pair. Why? Okay, if F was alone, let's say this disk is alone. That means F, right? F is the smallest guy, right? Is alone, right? And and now we have the other disks, right? Other files, right? Okay. Out of those remaining files, you choose the largest guy that fits with this guy. Okay. If there were no other files that fit with this smallest guy, right? That means okay, so you choose the smallest one and put it on the same disk, and then you have your remaining files here, right? Remaining files, right? If there are no other files that fit with F, then can that happen?
No,
Why?
because you're guaranteed to have at least one pair.
Yeah, okay. Because they say here, right? Assume that any optimal solution contains a pair that is put on a CD. So if none of the remaining files can be put on a CD with F with the smallest file, then how can you burn any other two files together? Right? Okay. Right. Yeah. So that means there must be some other files that can be burned together with F file. So then out of those, you choose the largest one, right? And by doing that, we didn't hurt the optimal, right? Then of course, in some optimal solution, then that characteristic holds, right? Okay. Okay. Right. So next one. The pair F1, F2, where F1 is the smallest file and F2 is the largest file, that's such that F1 and F2 fit onto one CD must be included in some optimal solution. True, right? That's a greedy step, right? Okay. I mean, we're talking about the nearest step, right? So we choose the smallest one and the largest one that fits with the smallest one, you put on one CD. That's obviously the greedy step, right? Okay. Next one, the pair F1, F2, where F1 is smallest and F2 is the largest file must be included in a pair in some optimal solution. Okay, so I would say it's debatable here because it depends on because of this word, some optimal solution. So yeah, so the reason is because like we know that this is true, right? The smallest file must be included in some in as a pair, right? But if the largest file does not fit with this guy, that doesn't contradict this, right? Because what this is saying is that we can choose F on a CD, that means smallest guy, and out of the remaining ones that fit with this guy, you put it on the CD, right? So that doesn't mean the largest file will be paired with F, right? So we don't really know if the largest file can be fit on a CD or not. So that's debatable, right? That's why I put debatable. Yeah, so the wording is bad. Okay, so the implementation of greedy algo. Okay, this is very easy, right? But because I need to quickly do the last question because that is more important than doing this one. This one is so I'll maybe record it like a 5-minute video and just send it to you. Very easy, right? How to implement it. Okay, so question number 4 and 5. So question number 4 and 5, activity selection problem. I'm sure that you have solved this problem on LeetCode code like 1,000 times, right? So you are given a set of activities, A1, A2, and AN, and each activity takes place during the start to finish, right? So start to finish. The finish is not included, right, in the activity time. Right? The two activities are compatible if, let's say, the start of one activity is at least to the right of the end of that previous activity, or the other way around, right? So two activities AI and AJ compatible if SI is at least FJ, means AI starts right after activity J finishes, or FJ is at least FI. That means AJ starts right after activity AI finishes. Very straightforward. Okay, so you've done this like 1,000 times, right? You've done this, right? You solve LeetCode questions, right? Have you guys done internships? So you have practiced LeetCode, right? Okay, so what are some compatible activities together? Quickly, can someone just shout out? Yeah, Chen Hong, right? So what are some compatible activities?
A1 and A2.
Yeah, A1 and A2, some more.
A2 and A3.
A2 and A3, yes. Okay, so A2 and A3 are also compatible, right? Because this activity starts at least as, I mean, to the right of the ending time of activity A3, right? That was it. Okay, so what are some incompatible sets? I mean, quickly, just A1 and A3, A1 and A3, right? Okay, so next question. Which of the following greedy strategies work? Okay, so AKA, you must be able to prove the exchange argument for these greedy strategies. Okay, so now I'm gonna tell some greedy strategies. So you tell whether it works or not, right? Okay, the better way of saying is that I'm gonna tell you some greedy strategies, right? You should tell me whether they're sensible or not, right? Okay, because like I said, right, the greedy choice must be sensible to you to even begin prove it, right? So I'll show some, and you tell me whether it's sensible or not, right? Choose the activity that ends last. Discard activities that conflict with A and recurse. Can this possibly lead to the optimal solution?
No.
Yes, no. Because why? I mean, okay, it's very easy, right? Here you have one activity that ends last, right? But you have many sub activities that are within this interval, right? And if you choose this guy, then you have to cancel away all the other small activities, right? Whereas you can choose all the small activities that lie within that activity, and you can get more, right? Choose the shortest activity and discard activities that conflict with A and recurse. Okay. At first glance, it may seem that it works because we choose the smallest one. That means okay, we are using the least amount of time. But then you realize that these activities are already in time, right? It's not like they're commutative. Like it's not like you're trying to adapt activities together, right? They are already set in time. So that means this will obviously not work because you have some scenarios like this, right? If you choose this guy, then you have to cut away these two guys, right? But had you chosen these two guys instead of choosing this guy, then you could have chosen two activities, right? Okay, this is an obvious question, but okay, so the correct choice is that out of the remaining activities, right, whatever you have, right, you must choose the one that starts the latest, right? Because intuitively, you know that activity will overlap with the least amount of activities. Okay, so intuitively, okay, intuition is one thing, but you have to prove, right? But of course, to start proving, you need to actually get a greedy choice, right? So by intuition, you know that. Okay, so out of the remaining activities, you better choose the one that starts the latest. Okay, and intuitively, you know that will overlap with the least amount of activities. Okay, okay, so you have to prove this formally, but let's do this step by step, right? Okay, so let's first prove the optimal substructure. Okay, so first let's prove the optimal substructure. Okay, so again, by last week, you know that we had to prove it by cut and paste, right? Okay, so suppose that an optimal schedule S includes activity J. Okay, so you have these activities, right? So A1, A2, whatever, right? So we have AJ and then A, right? So suppose that in this optimal schedule, okay, optimal selection of activities, that this optimal solution chooses this activity called A. Okay, then if you choose activity J, then we have some other activities left, right? A2, AJ minus 1, AJ plus 1 until A. Okay, so after you select one activity, you need to select the remain whatever you want out of the remaining activities, right? Right? Okay, so suppose that your okay. So we have n activities. So we choose one activity to be our answer. Then afterwards we have n minus 1 activities to also choose from, right? Right? And that means that will be a subproblem, right? So because we need to choose optimal, we need to choose activities from this set, right? After you choose one activity, we have n minus 1 other activities, and then your subproblem will be to choose from those activities, right? Okay. Suppose that oops. Okay, yeah. So suppose okay, now we have to choose activities from the remaining activities, right? So you can classify these activities into two sets. So this the ones that finish before AJ starts. So whatever activities that finish before AJ starts, and the other activities that start after AJ ends. Okay, so if AJ starts here, right, and then it ends here, then all the activities that come here, then you put it in before. All the activities that come after, you put it in after. Okay. Now, obviously, you have to choose an optimal schedule for before J and also choose an optimal schedule for after J, right? You have to choose an optimal selection of activities that come from that start before AJ starts, that finish before AJ starts. And you have to choose an optimal schedule from all the activities that start after AJ ends. That means from this, right? Because okay, for example, if you didn't solve before J optimally, then obviously you can choose a better solution to before J. That means you can choose more number of activities that finish before AJ starts and slap them on to your existing solution and get a better solution, right? So if you have a subproblem, that must be solved optimally. Because those activities are disjoint from all the other activities, right? Because we strictly separate them into before J and after J. So they must be also solved optimal, right? Okay, is that clear? Okay, so this is very easy, right? Is that clear? Like, is Hanju, is that clear? Sure. What do you mean sure? I mean, it should be obvious, right? As in, okay, so we chose an activity, right? AJ, right? And then after we choose AJ, we have n-1 other activities to choose from, right? Right? So can we choose all the activities after we choose AJ? No, right? We can only choose one, a subset of before J and after J, right? But we know that these activities are disjoint, right? So activities in before J and after J are disjoint, right? Oh, they are disjoint, and the other one is none of these activities overlap with each other, right? Is that clear? None of the activities in before J can overlap with activities in after J. Yeah, why is that? Sorry? Yeah, because these are the activities that finish before AJ starts, right? That means if AJ starts here, then they must have already finished by here, right? And then these are the activities that start after AJ ends, right? Then how can these overlap with each other, right? Yeah. Then that means this sub problem must be solved optimally, right? Must choose optimal number of activities from this set, right? And also choose optimal number of activities from this set, right? Because if you didn't choose the optimal, let's say you didn't choose optimal number of activities from before J, then you can that means there is some solution to solution to choosing activities from before J that is strictly better than what you ever chose, right? But then you can cut and paste. You can use that one, your current AJ, and whatever you chose from after J to get a strictly better solution. Yeah. Okay, so let's put the greedy choice, right? So suppose that we have the tasks. So T1, T2, T3, Tn, right? Ordered by the ascending order of start times, right? So that means this thing starts the first. Then that means this thing starts the last. So we have ordered in ascending order of start times, right? So this one starts the first, this one starts the last. Now we are going to process the activities in reverse order. That means we are going to choose the one that starts the last, then we consider the one that starts just before it, and then so on, right? Okay, so we are going to process tasks from Tn to T1. Okay. So this one is the one that starts last, and this one starts the first. Okay. Right. So here's what we're going to do. Okay, so we solved the activities by start time, right? So that means we sorted by start time, right? And then we are going to iterate through the activities in reverse order. So we're going to look at this one first, right? We are going to select the latest activity out of the remaining activities, right? That starts the last. That means, select the latest starting activity A star out of all the remaining activities. You edit your answer. And then you remove all the remaining activities that overlap with this guy. And then you recurse. Okay. So now let's see why this is correct to do. Okay. So this is a different type of proof, right? So previously we did exchange argument. This is also an exchange argument proof, but a little bit different. So you need to learn how to prove different types of greedy algorithms, right? Then only you'll be proficient enough to be confident for the final exam, right? Okay. So let OPT be an optimal algorithm, right? So in the optimal solution, it need not follow your own greedy solution, right? Like I said before, right? Our goal is to do a small greedy exchange argument and then prove that optimality is not correct. Okay, so our goal is to we want to transform the optimal solution of OPT to the greedy solution of G because we're doing greedy swaps, right? Without losing the optimality of op, right? Correct. Okay. So what does this imply? So that means at the end, OPT prime, that means whatever we transform OPT into OPT prime, right? S, that will be a greedy solution because we're doing greedy steps, right? Then OPT prime is G, where OPT prime is optimal because why? Each time we transform, each time we apply the greedy step into OPT, we don't hurt the optimality of OPT. then that means whatever you transform OPT into must also be optimal. And then that's also equal to G. G is a greedy solution. That means we have an OPT prime that is optimal, that is also greedy. That means your greed is optimal. Okay, so let's see how to do this, right? Okay, so now listen, right? So let task Tk be the first task, right? That your greedy solution and OPT will process differently. That means you're going from Tn down to T1, right? And let Tk be the first task that your greedy strategy and OPT process differently. Okay, so since Tk was the first task that G and OPT process differently, then that means G and OPT both chose the same tasks from Tk plus 1 until Tn. Right? Is that clear? Because Tk is the first task that G and OPT will process differently, right? And we are going back in time. That means we are from Tn down to T1, right? That means the tasks from this subset of Tk plus 1, Tk plus 2 until Tn must be processed the same. That means G and OPT chose the same tasks from that subset. Okay? Right. Yeah, so until this point, OPT was behaving greedily. Why? Because OPT did the same thing as G, right? G was greedy. Okay. So for G, okay, now listen, right? For G and OPT to process this task differently, it must be the case that Tk never overlap with any of the tasks that G and OPT both chose from this subset. Yeah, why? Why is that? Okay, I didn't put the answer, but okay. So let's quickly see why. If Tk overlap with any of the tasks that that G and OPT both chose from this subset, right? Then that means both G and OPT cannot choose Tk, right? Then that means both G and OPT process Tk in the same way, trivial way Tk. But we suppose that Tk is the first task that G and OPT will process differently. Okay, so that means Tk will never overlap with any of the previous tasks. Okay, that's the first observation. Right? And therefore, Tk never overlap with any task that G and OPT both chose from Tk plus 1 until Tn. Now, the next thing, important thing, because we are looking at the activities from Tn down to T1, right? Then out of the activities in T1, T2 until Tk, then Tk must be the activity of the remaining activities. So these are the remaining activities, right? Because we are processing because we have already assigned sorted these activities in increasing amount of start time, and we're going from back to front. Then that means Tk must be the activity that starts the latest, right? Okay, right? And then OPT and G acted differently, right? Then that means the only way that they can act differently is that because you are the greedy guy, right? So in the greedy guy, you always choose the one that starts the latest, right? Then that means G always chose Tk, right? But since you and OPT were behaving differently, then that means OPT never chose Tk. Right? Okay, so OPT never chose Tk. So then how would it look like? Okay, so I have given an example here, right? So here we, out of these activities, that means from Tk plus 1 until Tn, G and OPT chose the exact same task. So now we have these tasks, T1, T2, T3, T4, T5, T6. And T6 is the one that starts the latest, right? Okay, then this will be a Tk. So G will choose Tk, but OPT will not choose Tk. Right? Now, out of these tasks, right, that means out of T1, T2 until, okay, this disappears, right? Out of these tasks, right, I claim that OPT must have chosen at least one more. Why?
Not choose Tk.
Okay, that's true. But does that mean OPT did choose at least one more task from this T1 and T5? Yes, sorry, I forgot the name. Yeah, OPT is optimal, right? If OPT didn't choose, okay, if OPT didn't choose at least one more task from here, then Greedy has chosen one more task than OPT at least, right? Because OPT chose, sorry, G chose TK, right? And then from those things, or the two tasks, right? Then G and OPT chose the same task, right? Then that means Greedy has chosen at least one more task than OPT. If OPT never chose any task from T1 till T5, right? Then can OPT be optimal? No, right? Because there is some solution that chooses strictly more number of activities than OPT, right? Okay, so therefore, OPT must choose at least one more activity from these guys, right? Right. Then out of those activities, choose the one that starts the latest. Okay, so OPT chose some activities from these guys, right? Must choose at least one more guy. Out of those guys, you choose the one that starts the latest. Okay. There has to be an activity that starts latest, right? Okay, there is a total order, right? There must be an activity that starts latest among these guys, right? So call it T star. I call it T star, right? Yeah, I call it T star. Okay. Okay, so out of all the activities that OPT chose from T1 until TK minus 1, choose the one that starts the latest. You call this T star. Then we know that all the other tasks, whatever OPT chose from T1 until TK minus 1 without T star, if OPT even chose some, right, we know that they must start before T star in OPT. Right? Why? Why is that the case?
Because of compatibility.
Yeah, because of compatibility, right? Yes, because okay, so we have this subset T until 1 and TK minus 1, and T star is the one that starts the latest among all these activities, whatever OPT chose from that. Then the remaining activities, whatever OPT chose from T1, T2, TK minus 1 without T star, then they must start before T star, right? Okay. Then if they start before T star, then we know that exchanging T star for TK will not violate any other activities that OPT chose from T1 until TK minus 1 without T star. Because T star is the one that starts the latest among all these guys, right? And we know that TK starts even before afterwards, right? T star. Then if we remove this guy and put that guy into the set, then how can TK violate the validity of any of these stars that OPT chose from T1 and TK minus 1? Because they must start before T star and TK starts after T star. Then by swapping T star with TK, we will not hurt the validity of font. Right? So by doing the greedy choice of G, we converted OPT to OPT prime, right? By doing the greedy choice, right? And then OPT prime is also optimal. Right? So at each step, we interactively prove that doing the greedy step is safe. And if we continue like this, what happens is that at the end, we prove that OPT prime, whatever we convert OPT into, is also greedy. And that's also optimal because we didn't hurt that. Therefore, the greedy step is safe. Yeah, so that's how you prove it. Okay, so it was a bit rushed, but I hope you understood it, right? You can always check the recording, right? Okay, so let me quickly take the attendance as well. You can ask questions now. Gary is here. Ivan is here. Yeah. He is not here. Right? In fact, he's here. Oh, Brendan. That one is exception. Please go ahead. KJ. Ryan. Nathan. Okay. See you.